Are you ready for some Physics 71? Let's quickly review Newton's laws and applications and try a simple problem together, shall we? We now go through some key concepts, starting with Newton's laws. Newton's first law is all about inertia. A body maintains its motion unless acted upon by a net external force. If an object is at rest, it remains at rest. If an object is moving at constant velocity, it will keep moving at constant velocity. We can express this more formally as a vector equation with the sum of forces equaling 0. Next, force and acceleration. A net external force in a body produces an acceleration inversely proportional to its mass. We know this to be the familiar F equals ma. Oftentimes, applying this law requires us to solve it for each axis we're considering the motion in. For instance, we need two equations for the x and y axes if we have two-dimensional motion. Newton's third law is all about action and reaction. A body exerting a force on another experiences an equal and opposite force. If, for instance, you kick a ball with force AB, the ball applies a force FBA back at you in the opposite direction. So here we have Newton's laws. Next up, inertial reference frames. An inertial reference frame is any frame at rest or moving at constant velocity, that is, with zero acceleration. This is also a frame where Newton's laws of motions are valid and these statements are equivalent. Why should we care about this? Well, we need to be careful because in non-inertial frames, we sometimes see fictitious forces like centrifugal and Coriolis forces pop up in our analysis if we're not very careful. Now, next concept, mass versus weight. Mass is the amount of matter in an object and it is measured in kilograms. Weight is the amount of gravitational force felt by an object and it is measured in newtons. Here, we see the difference more clearly. This becomes apparent if we stand on different planets. On each planet, our mass remains the same, but the gravitational force can be weaker or stronger, leading us to have different weights. The last important concept, normal and friction forces. A normal force is a contact force acting perpendicularly from a surface to a body, and it's a measure of how hard an object is pushing on a surface. In fact, this force comes about necessarily as per Newton's third law. We symbolize this force by N. For example, we see that the ramp pushes with the normal force on the object. How about friction? This is also a contact force, but it is one that opposes the motion of a body. There are two types of friction, static and kinetic friction. These respectively arise when surfaces are at rest or in motion relative to each other. Friction forces are proportional to the normal force, which should make sense since the normal force measures how hard the surface pushes on an object. Static friction is denoted Fs and it is less than or equal to its maximum value, mu Sn. Meanwhile, kinetic friction is F sub k and is equal to mu Kn. Mu s and mu k are the coefficients of static and kinetic friction respectively. They both range from 0 to 1 and are a measure of the strength of the friction force. Also, we have that mu s is greater than or equal to mu k, so that F sub s is greater than or equal to F sub k. But why? Well, the answer is quite simple. This is because intermolecular bonds break more easily when surfaces are moving. Consider this diagram. If we push on a stationary object, the friction force matches the applied force up until its maximum value, mu Sn, after which the object starts moving and it's easier now to keep it in motion, which is why F sub k is less than F sub s. Here are the main concepts we discussed. Let's apply these concepts. You are riding with your friends on a sled going down a slope at an angle of 30 degrees. If your combined mass is 160 kilograms and the coefficient of kinetic friction is 0.50, how fast are you accelerating down the slope? So, how about you try this for yourself? Pause if you want, and I'll leave a countdown before discussing the solution. So, how do we approach this? So first, we assume an inertial reference frame. Newton's laws apply. We check whether there is a net force by drawing a free body diagram. And finally, we write out Newton's second law for the forces in our choice of axes. Let's first write out our given. Alpha equals 30 degrees, m equals 160 kilograms, and mu k equals 0.50. For our free body diagram, we are free to choose our axes anywhere we like, but it's convenient that we choose them along the ramp, incline. So, zooming in, the first force we need to take into account is a function of the mass, pulling the sled towards the ground. It acts vertically downward, and this is of course the weight. If we do a bit of angle chasing and imagine rotating this coordinate system, we can convince ourselves that this angle over here is none other than alpha. The next force we need to consider pushes the sled up perpendicularly from the ramp's surface, preventing it from just falling through. This is the normal force N. And finally, since we have a normal force and we are moving on a non-frictionless surface, we must have a force that opposes the motion downward. Indeed, this is the kinetic friction, Fk. Now that we have our free body diagram, we can write out Newton's second law. We have to write this for forces along the x and along the y directions. A bit of trigonometry gives us that along the x, the equation must be w sine alpha minus fk equals max. And since we're not accelerating along the y, ay must be 0 such that we get n minus w cosine alpha equals 0. So, these are the two equations that we have to work with. But recall that we can actually simplify this further by setting w equals mg and fk equals mu kn, so that along the x, we get mg sine alpha minus mu kn equals max, and along the y, we get n equals mg cosine alpha. Now, recall that what we wanted to solve for was ax. We can get this by substituting the second equation into the first, so that we get mg sine alpha minus mu kng cosine alpha equals max. After a bit of simplification, this finally gives us ax equals g quantity sine alpha minus mu k cosine alpha. And now we have our final equation. All that's left is to substitute our given values and we get our final answer. Ax equals 0.66 meters per second squared. That's all for me today. Thank you so much.